So we saw Kepler's first and second laws, and now let's move on to the third law. And this one's a little bit harder, I think, to understand for people because it involves this equation. Now, it's not a terribly horrible equation, but you do have to understand a little bit about it. So the Kepler's third law says more distant planets orbit the sun at slower average speeds. And the relationship between how long it takes them to go around, which is their orbital period, and how far away they are, which is actually more of an average distance from the sun, because remember, sometimes they're farther away and sometimes they're closer. So it's the average distance, which turns out to be the semi-major axis of the ellipse. And there's a relationship between the two that says that the period squared is equal to the average distance from the sun in AU cubed. Now remember, AU are those units that we use called astronomical units, where the distance between the Earth and the Sun, so the average distance actually between the Earth and the Sun, is 1 AU. So for instance, Mars has a distance of 1.52 AU, and Jupiter is basically 5 times farther away from the Sun than we are at 5.2 AU. So this relationship says really that the farther away your average distance is away from the Sun, so the longer that is, larger that is, the slower you move. Okay, so let's take a look at a simulation. Here we go. Let's switch it to Kepler's third law here, and we will get rid of the sweeps. Goodbye, sweeps. All right, let's go. So you can see how fast Mercury's moving, right? And everything moves in this simulation at the same. So when we zoom out to another planet, we'll see that it's going to be slower, right? Because Mercury's the closest to the sun on average. And you can see here on a plot that plots the period in years versus how the semi-major axis, which remember is that average distance away from the sun in AU. So right here, Mercury is 0.4 AUs away on average. Notice it gets a little closer here, a little farther here, but on average it's 0.4 AU away from the sun, super close. And its period is roughly between, something like 2.25 years to go around the sun. All right, now if we notice this curve here, I know it's kind of hard to tell, but this curve is that equation, right? P squared equals A cubed, plotted here. Okay, it's not a straight line. You can see that it's got some curvature to it. That's because this is not a linear relationship. If you remember that from wherever you learned about that, probably in high school. Okay, so let's go to the next planet and see. Zooming out, a little slower, right? And look where Venus is. Venus is farther away, about 0.65 AUs away, and a period about 0.6 years to go around. Okay, let's go up to Earth. Even slower, right? Because Earth in general is obviously farther away. It's 1 AU away on average, and it's very circular, that orbit, right? You can tell, pretty circular. Look at the eccentricity. We've said this before. Kind of hard to tell where it's closer and where it's not, where it's farther away, that is. But it fits on this curve, right? The Kepler's third law curve. Okay, let's move out again. Mars. Slower still, again, little 1.5 AU away from the sun, farther away than we are, and almost 2 years to go all the way around. Okay, now let's make the big jump out to Jupiter. There we go. Jupiter's slow, right? Yep, so Jupiter's period in years is, 15 or so here, right? A little less than 15. So yeah, about 12 years or so to go around. All right, zooming out, but notice everything's still on this curve, meaning it obeys this relationship, Kepler's third law equation. Okay. Actually, let's stay on Jupiter for just a second. I just want to mention something. So notice that there's no mass in this equation, right? There's nowhere to put the Jupiter's mass in this equation. And you might think, well, I know, and we haven't really studied this, but that gravity is what keeps Jupiter orbiting the sun. And you might think, well, why is it that that Jupiter's mass doesn't really come into this? Well, it kind of does, and we don't see that here in this equation because Kepler didn't know about gravity. Like, he of course knew there must be some force that keeps the planets orbiting the sun, because he figured out, he obviously believed in the heliocentric model, but he didn't know what that force was. And it wasn't until Newton came along, which we're going to study very soon, that they understood what the force that kept the planets going around the sun was. Now, once Newton got his hands on the equation, there is a place for Jupiter's mass in the equation, but it turns out that it varies as the sum of the two masses of, say, whatever the planet is orbiting, in this case the sun, and the planet's mass. And so what that means is if the thing that it's orbiting, right, or if one of the two objects has a lot bigger mass, right, so the sun has a lot bigger mass than Jupiter, then Jupiter's mass really doesn't come into it, because you have the sum of the two masses, and if one is just so much bigger, imagine you have a number that's like, 1,000 and a number that's 1. You don't really care about the 1, right, if you're adding those two numbers together. So it kind of doesn't make a difference. So, in other words, if Jupiter happened to be at the orbit of Mercury, right, at the same AU as Mercury, it would be whipping around the sun like crazy, like Mercury does, right? Let's remind ourselves how fast Mercury goes. All right, so it really doesn't matter that Jupiter has this giant mass compared to Mercury. It would still whip around at that speed because it would be closer to the sun. All right, let's keep on trekking out here in the solar system. Let's go to Saturn. Look at how slow that is. Again, we're still on this curve, right? So the farther out you are, the slower you go. And this guy has a period of like 30 years. I think we said that before when we were talking about people keeping track of things in astronomy in ancient days. Okay, how about Uranus? You can barely even see that's moving. It has a period of over 80 years, right? Because it's almost 20 AU out. Let's just keep going. Neptune. Wow. You have to wait a while or turn up the speed of the animation to see that thing go, right? And so here, if you look, it takes Neptune something like 170 years to go around the sun. It's quite a year. And Pluto. Again, can't really see it moving. And a period of, about 250 years. Because he's 40 AU out. But the point here is that Kepler's third law says, if the farther you are from the sun, or whatever you're orbiting, the slower you're going, the slower your orbital speed. Okay, let's go back to our PowerPoint. Oh, I think that is the wrong PowerPoint. Go away, PowerPoint. Okay, and let's try a question. Well, actually, you're going to try a question, so pause the video and answer the question.